So we're carrying on with our discussion of spanning tree, and as promised, here's our little network diagram. Looks a lot like the one in the overview video, and it pretty much is the same one, except I've labeled the types of ports that you have on a normal network. Now this bridge up here at the top, this switch is the root bridge. On the root bridge, by virtue of the fact that it is the root bridge, every port on the root bridge is a designated port, meaning that it will always forward traffic out all of its ports. None of them will be blocked, and we'll get into the blocked port state here in just a second. Now obviously both of these switches have two paths to the root. We have a path that's directly connected, and we have a path through the other switch. However, going back to our rules of the port types, these ports here will always be the root ports on these two switches because they are closest to the root. Obviously they're directly connected, so the port cost for those root ports will be lower than this designated port going through the other switch. So that only leaves this segment down here. Now obviously both of these switches are connected to this same LAN segment, and in order to reduce loops or prevent loops, only one of these switch ports can forward traffic onto this segment, because if both of them forwarded traffic, then the traffic would enter the segment here, leave there, loop through the root bridge, and you'd have a big loop on the network. So spanning tree looks at both of these switches and say, okay, you're both connected to this segment. However, this switch has a lower priority. Maybe it's configured as the backup route, for example, the route secondary. Well, since this has a lower priority, then I automatically win. You're going to block your port, and so this port on this switch over here is now blocked. It will not forward traffic onto this segment down here at the bottom. And so hopefully with this little diagram, the roles of designated ports versus root ports versus blocked ports are a little clearer. And again, once we see this in the lab, that's when it really clicks for me, and that's when it really clicks for most people, to be honest. So let's move on, and let's talk about the way switches communicate their spanning tree information. Switches communicate spanning tree using BPDUs, or Bridge Protocol Data Units. If you've dealt with switching for more than a couple of weeks, you probably have seen references to BPDU, most likely on switches that are running BPDU guard on their edge ports. And if you're like me, you wonder, what's a BPDU guard? So you go out and Google BPDU guard, and that may lead you to a discussion of exactly what is a BPDU, and essentially that's what a BPDU looks like on the wire if you were to pull it off the wire using Etherreel or something along those lines. Every 2 seconds, every switch forwards a BPDU out every port that's connected. And you really don't need to know about any other type of BPDU for the CCNA exam other than the Hello BPDU. And in fact, you won't be quizzed on these fields that I'm about to go over here over the next few seconds, but I found it makes a lot more sense when you discuss spanning tree and BPDUs in general if you know where all this information comes from. So you'll notice that we have the version of the BPDU, we have the BPDU message type, and again there are other types besides hello, but that's all we're going to really worry about for this exam. We also have fields that tell the receiving switch, here's who I think the root is, and this can be me, or it can be whatever other bridge or switch out there that actually is the root of spanning tree. It has a field to tell you how many hops or what's the path cost to get to the root. Here's my bridge ID, here's who I think I am, and here's the port that I'm connected to you on. You also have fields for the maximum age and the hello timer and the forward delay, as we discuss elsewhere in the course. So as you can see, spanning tree is a pretty chatty protocol. It tells you every 2 seconds, hey, here's the root and here's who I am. And so you see that pretty quickly any changes to the root bridge gets communicated all the way down the line to the furthest point on your network. And that's pretty much the normal spanning tree operations. Switch starts up on the network, starts sending hello BPDU packets immediately. It identifies itself as the root because as far as it's concerned, it's the only person in the entire universe. I'm the only switch, and so therefore I am the root. Neighboring switches receive this BPDU. If the advertising bridge ID is lower than the current root, replace my root bridge ID and start advertising the new root bridge. So if this switch comes on the network, and it is actually indeed an older switch, or it's got a lower priority, or it wins the election to be a root bridge, then the neighboring switches will send that new root bridge information out to the rest of the network. So you can see that pretty quickly, if a new root bridge comes on the network, within just a few seconds, all of the switches on the network know about it. By default, the BPDU packets are sent every hello interval, and the hello interval by default is 2 seconds. We'll get into some of those intervals in the lab whenever we look at some of the spanning tree configuration commands. And pretty much it's lather, rinse, repeat. Every 2 seconds, send out a hello BPDU saying, here I am, here's my route, here's the quickest way that I can get to them, and everything just kind of works. So the last thing we'll talk about are spanning tree port states. Now these are different than the spanning tree port types, and that will become apparently and abundantly clear here in just a second. The first port state is the blocking state. When you power up a switch or you plug a network cable into a port, it starts out in blocking state for up to 20 seconds. In this state, the switch is not doing anything except listening for BPDUs. If a switch starts receiving BPDUs, then it knows, hey, another switch is connected on this port, so I need to start the next state in my spanning tree port progression, if you will. Now again, it sits and listens for 20 seconds, so if you've connected a workstation to a particular port, obviously that workstation is not going to send BPDUs, so the switch is just not going to forward any traffic in or out of that port for up to 20 seconds. Most workstations, most modern workstations, will have booted by that time, at least up to the point where it's attempting to use DHCP to gather an IP address, or if you're on a Microsoft network, it's attempting to contact a domain controller or a Novell Directory Services server, or so on and so forth. At any rate, for most situations, this 20 seconds will cause the workstation to time out and just carry on booting. There's a way you can get around that, and we'll talk about that when we discuss some of Cisco's proprietary extensions to 802.1d spanning tree. However, if a switch does hear a BPDU, the switch goes into the listening state. Really, the only functional difference between blocking and listening is that the switch is actually processing any BPDUs that it receives. So essentially in this state, the switch is listening for how many switches are actually connected to this port. You could have a hub and have 5 switches connected to it, or you could just have a single switch. After 15 seconds in the listening state, the switch moves on to the learning state. The switch listens to both BPDUs and frames from the other devices, but it only uses that information to build the MAC table in that switch. It essentially uses the learning state to determine, is there a loop in the network? Am I learning MAC addresses on multiple ports? And if so, then I just need to turn this port off because there's obviously a loop and I don't want there to be a loop in the network. That's my whole purpose in life, to prevent loops. So it sits in the learning state for 15 seconds, and after 15 seconds in the learning state, the switch finally moves into the forwarding state. So you can see by adding up these times, you can connect a switch to a switch port, and it could take up to about 45 seconds or so before the switch actually starts utilizing that switch port. Now, in the event of a network failure, that's 45 or 50 seconds where no traffic's getting moved about the network, especially if one of the links that failed happened to be a link back to the root bridge. Like I said, a lot of in-depth stuff for a protocol that most of the time just works and works out of the box and works pretty well. And this concludes our in-depth discussion of spanning tree.